Uh, Hello. So this is the last screencast segment associated with lecture series number 7, which is a discussion of the so-called central processing unit instruction cycle, otherwise referred to as the machine cycle. Some people refer to this cycle as being the fetch, decode, execute cycle. It's one and the same thing. And in the last part of this lecture series, we actually go through an example of a hypothetical instruction, right? Hypothetical instruction to try and understand the key phases associated with the so-called instruction cycle, machine cycle. Great. So, a brief recap. Maybe we should have done a recap at the beginning of the lecture series as well. But if you remember, so-called software or computer programs can be viewed as being composed of notations that are either associated to what we introduce as high-level languages or low-level languages, right? And we emphasized the idea that this notion of high versus low-level language is really linked to the level of abstraction. So how close to the native machine code the language is. The higher the abstraction, the further away that language is from the native machine code in terms of the notation. The higher the language, the more intuitive the notation is for human beings. So human beings, otherwise known as computer programmers or software programmers, by the time you get to second year, I guess, would typically write computer programs using high-level languages, right? Using a notation that they can easily interpret, or a notation that they can easily understand. And usually this notation is linked to any language of choice, right? It could be English, for instance. I'm saying language of choice because I do know that there are certain computer programs I do believe that are in these other languages. I would like to think that the Chinese probably have, I should look this up, but I think so. It should be the case. I don't know, but that besides the point anyway. The key takeaway thing here is that programmers will typically write programming languages in a high-level language notation. And we discovered that we have so-called language translators that will typically be used to translate a notation that is in a high level, a notation that makes use of a high-level language into a notation that a computer will be able to understand, a la machine code, so-called ones and zeros. The machine understands a notation similar to this. It does not understand this. In certain instances, programmers will write computer programs using low-level languages such as C or assembly language code. Again, assembly language code is in a notation that is somewhat intuitive to human beings, although it's not as easy to interpret as a high-level language. The idea behind assembly language code is it's the closest we can get to the machine code. It's the closest intuitive notation that is associated with the machine code, right? And in fact, a single instruction that's associated with a single instruction in assembly language can be mapped onto ones and zeros that a computer will be able to translate. That's not the case for a high-level language, right? So what we're saying here is that the add what's in register, also add what's in register 8 with what's in register 9 and then put the results in 10, right? This is what this instruction does here. This instruction here can easily be mapped onto a stream of ones and zeros that are 2 bits in size. And it is this stream of ones and zeros that a computer executes, right? Very simple ideas, but extremely powerful. I keep mentioning that they're simple ideas because really, if you think about it, these are very simple ideas. We've gone back to grade school here, right? Primary school, where we are talking about addition, subtraction. And this is what we're going to be doing really once we get to a stage where we look at the MIPS assembler, right? It's addition and subtraction of numbers. The only difference really from what we did in grade school is that the addition and subtraction follows certain rules and procedures, right? So instead of saying A is equal to C plus B, you're saying add, and then you say C comma B comma C, right? So this, by the way, what you have here, Jesus Christ, what you have here is similar to something like, in fact, this could easily be rewritten as this. 10 is equal to, this is what this instruction means. Not that it matters here, but I guess hopefully this will help people kind of like understand what we are working towards here. I should work on my annotation skills using my mouse. So $8 plus, wait a minute, maybe this is a good time for me to showcase my skills associated with, I don't know if I introduced this in the previous screencast, but it turns out that, let me show you something here. It turns out that, this is connected already, good stuff. It turns out that I can literally convert my I can literally convert my where's that thing? I can use my phone as an input device, right? So maybe this would be a lot easier. I'll just say remote input, boom. I'll move this here and just click, move it here, and then I'll just say and this is not working, is it? I'll just have to use my mouse, I guess. That's fine. So, but anyway, this is literally equal to $10 is equal to $8 plus $9. This is what this notation means. And by the way, all of these different notations will make sense very, very soon, right? Great. So we're just going to go through a very simple hypothetical illustration. Now, to make it a lot easier for us to understand, I'm always tempted to use actual specific MIPS assembler instructions, but we've kind of dumbed it down to make it a lot easier, right? But the idea is the same. So we've abstracted how MIPS actually works so that it's a lot easier for us to understand. So let's say we want to, here's an example of how this whole notion of, before we get the example, this whole notion of decoding of instructions from this notation to this notation. It turns out that our example is an add instruction, MIPS add instruction. And each MIPS add instruction, by the way, has a corresponding opcode, right, which can be translated into ones and zeros, right? But the way this works really is that the conversion from this variation from MIPS assembler to machine code, it's quite trivial really. Each one of these different components associated with the instruction, right? So add, $10, $8, $9, conform to a certain standard, right? So an instruction, an instruction is composed of 32 bits in MIPS assembler, and those 32 bits are generally associated or mapped onto specific bit segments, right? So the six bits here, right, will conform to the so-called opcode. The bits here, the 5 bits here will correspond to so-called source register. The bit stream here, which is 5 as well, conforms to the target register, right? So these are the things that hold the operands that you'd be adding in the case of the add instruction. And then RD is just the destination register really, right? So if you notice here, what we are doing is really just substituting, using this example here. Using this example, we're just trying to provide a mapping as pertains to MIPS, right? So the add comes here, source register is 8, target register, which is also called source register number 2, is 9, destination register where you put the result is 10, right? At this stage really, at this stage, at this stage, these bits are normally associated to the register numbers, right? So this is register 8. We haven't gotten to a stage where we're actually making reference to the contents of the register. We're just making reference to the register number. Right? Don't worry if this is not making sense at this point in time. It will make sense in due course, right? But the idea behind decoding is once you map all these different components that make up the assembly, the MIPS assembly language instruction, you can then decode the instruction. How? Because you know that each operation has a corresponding opcode. So in this case, the opcode is 00, right? The register number, just take note of register number 8, number 9, number 10 here. The shift amount here is 0 because it's only applicable to specific types of instructions. Just play along. And then the funct code. The funct code is normally associated to so-called R formatted instructions, right? Because it turns out that they are the bulk, they make up the bulk of the instructions. So to make it a lot easier to have a number of permutations that can later on be mapped onto these 200 or so instructions, you just say this is going to be 0, and then you only change the funct code for only R formatted instructions, by the way. But once you identify these different numbers associated to these components that make up the MIPS assembler instruction, you can then come up with a binary representation. All you're doing is you're just converting these to binary, right? So 00 converted to binary using 6-bit representation, because we're saying this can only take in 6 bits. It's just going to be a stream of 6 zeros. You convert 8 to binary, and then you come up with this, right? Using 5-bit representation. You convert 9 to binary using 5-bit representation, 10 to binary using 5-bit representation, 5-bit representation using the shift amount, and then 6-bit representation of the funct code. Now the funct code is there. It's already available. All you do is you look up the manual, right? Funct code is there. And you notice that the funct code is only associated with R formatted instructions. Again, don't worry if this is not making sense at this point in time. So anything that has a funct code is R formatted. If you notice, anything that has NA, which is not applicable, is R, it's I formatted. Right? Anyway, it's either I formatted or J formatted. So there's fundamentally in MIPS you have R formatted instructions, I formatted instructions, and J formatted instructions, right? So hopefully it's going to make sense, right? So the funct code for that example that we have is coming from a lookup table that we have access to. Any manual have that, all those details. All right. So again, I was just mentioning here that we get to a stage where we have now 32 bits. So if you add 6 plus 5 plus 5 plus 5 plus 5 plus 6, you come up with a stream of 32 bits. Now this 32-bit representation really is composed. I'm trying to figure out what I was saying here. Right, so okay, I was just trying to. So just to mention here that once you decode this instruction, right? Once this instruction is decoded from this notation to machine code, as we have it here, this was just a note to remind us that the actual fetching, again, we abstracted so many different things here, but they will make sense eventually. The actual fetching, right, is done 18 bits at a time, really. So when we came here and said, when we got to a stage where we're saying, oh, fetching involves identifying the address and whatnot, you see, this memory is byte addressable, right? So the stream of 32 bits is fetched, it's fetched 8 bits at a time, right? So when this instruction is being executed, as you are going through that fetch, decode, execute, store cycle, in each cycle you pull 8 bits associated with that instruction. So in cycle number 1, you pull these 8 bits, and using these 8 bits, actually, the CPU will be able to, if it's MIP centric, it will be able to tell to say, oh, this is actually an add instruction. because it will count 1, 2, 3, 4, 5, 6. It says so 0, 0. Oh, if it's so 0, 0, then it's an R formatted instruction, right? If it's an R formatted instruction, then it will expect to, it will be able to translate what sort of operation needs to be done once it has access to the funct code. Okay, great. So the whole idea here is that the instruction that will be executed is something similar to this. So if you're adding two numbers, for instance, you'll be doing this, right? And of course, behind the scenes, the bit segment that represents the source register and the target register would have to be identified. So using that value, you'll be able to identify what needs to be fetched from main memory, right? Great. So before we get to the example here, right, just remind us, we are just going to make reference to some special purpose registers that have already been introduced, but to remind us that the program counter, this is like revision 101, we've already discussed this, the program counter keeps track of the next instruction to be executed. The MAR, or the memory address register, is nothing more than an address in memory that is currently being read or written to. So it's being read if you are reading something. It's being written to when you're writing a result of a processing step. The memory buffer, buffer register, or otherwise referred to as a memory data register, right? Which is one and the same. It will hold the data that is being read from main memory, or the data that is being written to in main memory. Observe here, right? The address registers are different from these buffer registers. Why? Because the address registers are solely concerned with addresses associated with the data that's being processed. The data registers, the buffer registers, are concerned with the actual data. And really, we discussed this during the rundown we had on the different types of buses. Address bus, data bus, control bus, right? Keep note. And then the current instruction register will hold the instruction that has just been fetched from main memory. I hope this makes sense here. And then finally, the control unit will decode the instruction itself, try and make sense of what needs to be done. And then the ALU will perform the actual arithmetic, why am I saying mathematical? Arithmetic operation, or the logical operation. We always emphasize the fact that these are arithmetic operations because these are simple, primitive operations, add, subtract, right? It's nothing complex here. If you're performing a complex operation like let's say if you use your calculator, for instance, imagine using your calculator, right? In this case, I'll use my calculator to say I want to find the square root of, oh wow, that's weird. Square root, where's the square root here? Maybe I should change the setting and change it to scientific mode. Nope. Yeah, I thought I did convert it to scientific mode. Okay. Maybe I can numeric. I haven't used this calculator in a while. It's weird that I can't find it's weird that I can't find square root. Simple notation, statistics. Probably won't work. Wish I could. So I wanted to use the example of a square root here, square root function, because it turns out the square root function, if you're getting a square root of a number, it's a much more complex thing that's happening there, right? But behind the scenes, what the CPU will do is it will, the instructions that are responsible for performing the square root of a number, they're dumbed down to a very basic level, very primal level, right? Where you're just working with addition, subtraction, multiplication, and division. Right? And if you think about it, really, that whole operation of getting a square root of a number or a square of a number can be viewed as being a series of different primitive mathematical operations. So this is what the CPU does behind the scenes. But anyways, so we're just going to look at a very basic example. Again, this is abstracted. And this example is going to consider what typically happens when you're, let's say, adding two numbers, right? So your typical assembly language code would be, again, this is this is not MIPS, it's hypothetical, right? But the idea is the process you'd go through for you to add two numbers is you'd use a series of load instructions where you load data that needs to be a part of the operation into main. If you load it from main memory, right? Then you add the value that has been loaded in main memory, and then perform your computation or your operation, and then you store the result. Fundamentally, this is what you do. So this is what we're going to simulate. We're just trying to understand exactly what happens behind the scenes. Just going to pause here and think if maybe we should, at some stage, maybe we should use an actual MIPS instruction. Maybe we should. We will, I think. Maybe in the tutorial, I think we will use an actual MIPS instruction. That'll be good. But the idea here is that if you were wanting to perform a high-level operation such as this, right, it would be dumbed down to equivalent assembly language instructions similar to this, right? And the reason, by the way, where we would want to have a representation that's similar to assembly is because assembly language helps you understand the different things that happen to the instruction. Jumping to ones and zeros will make it tremendously difficult for us to figure out what's happening, because we would need a firm understanding of how this bit representation is done, what the different segments are mapped onto and whatnot. But if we move from a high-level representation, which we can understand, to assembly language, we can better understand exactly how these ones and zeros are interpreted. Right, so we're going to assume that all these different, remember this instruction is in main memory at this stage, right? You want to perform this operation where you're adding two numbers. The instruction itself is going to be in main memory. Whenever a program is loaded into main memory, each of the individual instructions are uniquely identified using an address. We introduced this idea. So there would be an address associated with each instruction. So the load instruction, load this address, would be associated, in this case, we're associating it with memory address 100. Of course, the addressing is not as simple as this, but again, we are abstracting this. Add 104, or add the value at address 104 is associated with 101, address 101, and then store 105 is associated with address 102. You want to remember these things, right? So that they make sense. And then for our hypothetical example, what we are further saying is that the numbers we are adding are 1 and 9. So 1 is located on memory address 103. 9 is located in memory address 104. Great. So we're saying that the first thing that happens during the fetching, we are still at the fetching phase here. Initially, before anything is done, the program counter will point to the next instruction to be executed. As part of the fetching phase, the first thing that will happen is the value that the PC points to, the address, the current address to be executed, the current instruction to be executed is at address 100, right? Current address to be executed is pointed to by the program counter. We mentioned that as part of the fetch phase, control unit will copy contents of the program counter to the memory address register. So this value is copied to the MAR. And then the address in the memory address register, the actual value here, which is 100, is going to be used to fetch the data. So the value that is in the MR, in the memory address register, is the register value in memory. Using that register value in memory, you will fetch the actual data that is on address 100. And what is the data or instruction that is on 100? It's the instruction 100. It's this instruction load 103. Remember here, you're going to see a situation where data and instruction are, the words data and instruction are sort of like making reference to the same thing. The reason we are doing that is because of that wonderful concept called the stored program concept. Both data and instructions are stored in the same location, in main memory in this case. So we come here, right? We say the instruction that's at here is going to be loaded into the MBR, which is the memory buffer register or memory data register. And then at this point, right, the program count is going to be incremented by 1 so that the PC now points to the next instruction to be executed. All right. And then the memory buffer register will load the value of data or instruction that was mapped onto what was in the MAR into the current instruction register, CIR. And then the control unit will now decode what is in the CIR. And remember, the decoding will be trying to make sense out of what exactly needs to be done. And remember again, because we are abstracting all of this, these would not be actual load 103 or 100. These would be streams of ones and zeros, right? So the control unit will then decode the stream of ones and zeros that maps onto this load 103. And then we'll be able to figure out, say, okay, so what needs to be done now is we need to load data that's on, we need to load what is in register 103. And you'll notice here, right? I have a corresponding mapping, by the way, of the values in main memory here. You'll notice here that once the CPU decodes to say we need to load data that's in 103, you can immediately see that in 103, we actually have the value 1. Great. So then what the CPU does once it decodes this, it will realize, oh, we need to load what's in memory address 103, and what's in 103 is the value 1. This is data now. It's actually data. These are instructions. This is data. Both data and instructions are stored in the same location. So at this point, the data that is in 101 will be loaded into the accumulator, which is the 1, right? Okay. So this is part of the decoding process. And then the control unit then, like we said, decode this to determine what needs to be done. So it will realize that instruction needs to be loaded from memory location 103, which is 1. So this data will now be copied to the MBR. Remember, again, because we are viewing instructions as data as being the same, which is why what we are loading in this MBR can either be an actual data or instructions. It's one and the same thing anyway. And then we've done the execution here. The execution will just involve copying here because we're just loading the value in the accumulator, right? It's a load instruction. So the loading itself, execution of the load instruction will involve copying that value 1 into the MBR. I mean, it's the accumulator rather, right? So we would have executed the instruction. And then you notice that at some stage, right? At some stage, we said the PC was incremented by 1. When the PC is incremented by 1, it moves from 100 to 101. And you will notice that the address 101 is associated with the instruction add 104. So I'll go here. Because the PC is pointing to 101, the value 101, the address 101 will be copied to the memory address register. And remember here, if you look at this, the top here, we are now in cycle number 2. We were previous in cycle number 1, which involved the instruction at memory address 100, right? Cycle number 1, decode, execute, and then cycle number 2 involves the address associated, the address 101. Right? So 101 will be copied to the memory address register, and then the address in the memory address register will be used to fetch the specific data from main memory. And we'll realize that, oh, what is actually on 101 is this instruction called add address 104. Right, so that instruction is going to be returned data bus and then copied to the MBR. Again, the PC is going to be incremented by 1. When it's incremented by 1, observe what's happening here. It was previous 101. It's incremented by 102, and you'll notice that 102 is going to be a store instruction. But we're still in cycle number 2, right? We push this instruction add 104 into the MBR, and then what is in the MBR is going to be pushed to the current instruction register, right? Because the current instruction register will have the thing that needs to be executed. Sorry about that. And then the control unit will decode what's in the current instruction register. Once it's decoded, it will realize, oh, I need to execute the add what is in 104 instruction, right? And what add in 104 will mean that I'll need to, because it says add what is in 104. So it will need to check what is in 104, right? What is in 104 is going to be copied to the MAR value will have 104, right? Because it says add to 104. And then what is in 104 is going to be pushed to the MBR. What is in 104 is 9. And then finally, because we're saying add 9, we'll be adding what was in the accumulator. There was 1 in the accumulator. Once we say add 9, then the value will be 10, because we're adding 9 to 1, which was in the accumulator. So we are done with cycle number 2. Cycle number 3 now, right? Cycle number 3, we involve, because the PC is now pointing to 102, address 102, we're now going to handle the thing that's located on address 102. It turns out that it's a store instruction. Store is nothing more than, you can view store as being writing to a memory location, right? So contents of the PC again are copied to the MAR, which is 102, at which point the PC is going to be incremented by 1, right? And by the way, the addressing here is a bit confusing, because you might think that in the second cycle we need to execute 1, but this would be different, obviously. But just play along here. So what is in 103 is, what is in 102 is store or write to memory location 105. Again, the address is going to be copied to the MAR, which is 102, and then data associated with this location, which is just store 105, will be copied to the MBR, and then the PC will be incremented by 1. The MBR value will be pushed to the CIR, which is the current instruction register, in readiness for execution, at which point the execution just involves writing to a memory location. The CPU will decode that, right? Remember, this is a stream of 1 and 0. The CPU still needs to decode what needs to be done, and then CPU will realize, oh, so we need to write to a memory location, and it immediately knows what needs to be written is what is in the accumulator, what is currently in the accumulator, and the accumulator is nothing more than a temporal storage location on the CPU. So what is in the accumulator is the number data 10. It will be written to memory location number 5. Yeah, CPU decodes the instruction to determine what needs to be done, and then you know that you need to store the results in 105. And then you execute that. The execution signals the end of the cycle itself. So you will notice again here that for us to actually, I'm just going to go back to the initial thing here. For us to carry out this instruction, we went through 3 iterations or 3 cycles. Load, add, write, right? 3 instructions, 3 cycles. There are 3 cycles, each mapped onto fetch, decode, execute, fetch, decode, execute, right? Okay, so just to recap here, I just wanted to point your attention to the important things associated with this illustration here is the fact that depending on the type of instruction, it might involve numerous cycles, right? In certain instances, it might involve much more than 1 cycle. It might only involve It might only involve maybe 1 or 2 cycles, right? But the key thing is just to be familiar with the key aspects associated with this fetch, decode, execute cycle. What actual operations occur in these different phases, and how does the location, how is the location in memory, how does that feed into this fetch, decode, execute cycle, right? There's a difference between a memory address and the contents of that memory address. But the interesting thing is, both of these things are associated with main memory. Another interesting thing is that both the data and the instructions are stored in the same location. All right, so just to recap the entire lecture series here, what we're saying is that the key phases associated with the so-called CPU instruction cycle, the machine cycle, are just 4 of them. The first stage, or step number 1, is the fetching of the instruction, and then step number 2 is decoding. Then comes execution, and then storage, right? That's the basis, really. The other takeaway point really is the key hardware components that are involved here. And in certain instances, especially during this illustration or the walkthrough, the specific types of special purpose registers that are involved in this process. The PC, MBR, MAR, the accumulators, the current instruction register. Those are all special purpose registers that have specific functions during the fetch, decode, execute, store cycle. So in closing, I thought I'd just tie this to what's coming our way very, very soon. It turns out that in as much as we've abstracted this so-called machine cycle, CPU instruction cycle, but there are a lot of gory details behind the scenes. It turns out there are a number of moving parts. So what you're seeing here is different phases associated with the instruction cycle. IF, by the way, is instruction fetch. ID, anything with IF here, tagged as IF, is instruction fetch. So this would be instruction fetch. Anything tagged as ID would be instruction decode. Anything tagged as EX would be execution. Anything tagged as mem would involve writing to main memory. So those 4 phases. I know it might be a bit confusing right now, but I wanted to mention that if you look at these different components, because we were abstracting, right? Because we were abstracting what we were doing, but it turns out that there are other hardware components that we didn't mention, but we will mention them initially. It turns out that the fetch decode cycle itself involves a number of different things. So we mentioned the program counter, the PC here, but it turns out that there's a hardware component called the adder. It's the one that's responsible for the process that involves the incrementing of the program counter is done by the adder. There's an adder on the CPU. All of this is happening on the CPU, by the way. So there's an adder. There's a separate instruction memory. There's data memory, right? There are components such as the register file, which has a mapping of the different registers associated with that piece of hardware. In the case of MIPS, right, we'll look at QTSPM very, very soon, but in the case of MIPS, you have access to a number of registers, not just the special purpose registers like the program counter here, but there are status registers. There are also general purpose registers, right, which you use to play around with data. There's actually more when you're working with floating point numbers, right? All of this will make sense very, very soon. But key takeaway point from this slide here is that it turns out that there are a number of other components. The sign extend, for instance. We get an appreciation of what that thing is all about. Multiplexers, these things you are seeing as maxes, right? Anything labeled as a max is called the multiplexer. The ALU, right? And by the way, the reason why we have some of these components is because if you think about it, what we are saying is we have this fixed hardware platform that works or that is operated on using a fixed set of instructions. But because you have a fixed set of instructions, there are certain things that will only be applicable to specific types of instructions in that instruction set, right? So some things will not involve the sign extent. Some operations will not involve the sign extent, right? Some operations might not involve this particular multiplexer that's sitting here. This is only applicable to the J formatted instruction, the jump instruction, by the way. Great. I thought that was really interesting. I did that in part to two reasons why I decided to speak about this, to give you a sneak preview of the bigger picture and to highlight how interesting this whole thing is, right? The computer system works, modern day computer systems work using very elementary principles, but there are a number of different steps or operations that are performed behind the scenes. Great. So I'll see you in the next lecture series where we get to discuss peripheral devices, which is lecture series number 8. This should be week after next, I believe. Or is it the other week? All right. Thank you. I'll see you and please take care.